Okay, let's continue. So we saw the score matching advantages. How to sample. So we discussed how we can evaluate, how we can optimize and whatnot, but how to sample, because that is always a question with energy-based models, because we don't really have a prescribed probability distribution. We must determine a procedure for sampling. And as we saw, like for RBMs, one way was, well, MCMC. MCMC and Gibbs sampling, with Gibbs sampling specifically. Another way is exploiting Langevin dynamics, which shows another MCMC-like procedure. So during training, we generally don't have this sampling. After training the score-based model, we sample with Langevin dynamics as follows. We start from, well, the Langevin, let's say, equation is that every new sample is basically derived from the previous sample, like the same sample in the previous time step, plus the score function scaled by epsilon, and a noise variable z scaled by the square root of 2 epsilon. This Langevin dynamics procedure, you don't have to, like, no need to go into the precise details, but it can be shown that if you follow this iterative procedure, you can start, you can obtain basically in the limit. So as epsilon goes to 0 with time, and for many steps, you obtain samples from the actual distribution, the true distribution. This is an iterative process. So let's say at t0, let's say we call this a 0, so we start from the noise variable. We obtain the score function estimate, right? So that's at t0, and and t plus 1 we use the previous one, so x0, and then for x2 use x1, and for x3 we use x2, and so forth and so forth. And as you can see, we start spread out, so because it's random noise in the beginning, and with time, as we go to k, we start sampling from the relevant portions of our data space. Again, to the limit, we are guaranteed to start sampling from our true distribution. So by many iterations, we will obtain samples from our, using the score function, we're going to start getting samples from our true score, data score. Langevin yes?
Sorry, but epsilon is a hyperparameter, right?
Yes.
So we define it, but it doesn't change every time. So how can we say that?
You do annealing, over time. So I think normally it should be t here. Yes.
Okay.
But in practice, so normally you do t. I don't remember if in diffusion model you have to, because it depends. I mean, okay. So this is something also similar to SGD, right? Like in SGD, you also have the lambda hyperparameter, and in theory, like to actually have the model converge, you need to anneal it in a similar fashion. But in practice, it works just as well. I think here you anneal it for that reason, actually, because in the end here you don't care about just like optimization, but in the end sampling from the distribution. Right. So Langevin dynamics was originally proposed in the context of molecular, like the model molecular dynamics, similar to noise SGD. You can think of it like that, right? So we are updating parameters, given your previous parameters, applies a scaled version of your gradient, plus some noise. And if you do like that, it was also, it can be connected to Bayesian learning. There's a very nice work by Max Welling and Yi Wai-Te. The intuition, you can think of it as given my current sample. So let's assume that my sample is not great, it's not good enough, but so it's not great, but it is good enough. I am using my score function to move to a new sample that has a bit higher probability of existence, right? So if I am in a okay place, where if I go that way or that way, here is going to be closer to maximizing my likelihood, so I move one step here. And now I am in a better log likelihood step, like position. What could be the problem with this process? Intuitively. So let's say I've got like probability 0.1 here, and then I say if I move like one step here, it's going to be 0.2. What's the problem with this algorithm intuitively? Sort of. It is very local. Because we're minimizing in the end some form of Fisher divergence, we emphasize regions. So in the optimization, we will optimize. In the optimization, we'll emphasize regions with high likelihood because these regions are the ones that influence the most our loss function, our optimization function. So the problem is that in high dimension, most space around us will be basically empty, will be basically zero. And if it's zero, then the Monte Carlo estimation will be not accurate enough. So our samples will have very high variance. And this is what you see here. So these are the true data scores, and these are the estimated scores. So this is like if I had my ground truth, like let's say in this toy example. You can see that it is very accurate. The score estimation is very accurate on those locations where P of x is high, but inaccurate in all other locations where basically my likelihood is very low. Because you have to think about it. It's like to think about, like, that's the optimization, right? So if you were asking the model to optimize this, the model prefers to focus on these regions because in the end, this will what matters in the end for this integral to go down. If it's really good here, but mediocre here, it doesn't matter, like it's actually worse loss. So in the end, the model is implicitly encouraged to focus on the very high density areas. Now, normally that would be okay if we wouldn't care really about the low density areas. However, the problem is that in high dimensions, because of the curse of dimensionality, most areas are empty, and not because they're unimportant, it's just because of the curse of dimensionality. Like in very high dimensional space, basically everything is empty. So the model has wrong incentive. There are some, there's around the manifold, low dimensional manifold, there is some space that it makes sense to optimize, but this doesn't mean that everything else is necessarily garbage. So we want to define a process, a better optimization process, to make sure that the model doesn't ignore completely low data density areas. Is this clear? And before explaining how we can fix that, how it was proposed to be fixed, this is also a problem with sampling. So when you've got Langevin sampling, you've got a very local rule. When, again, here, That's not the same problem, but it's similar. It has like a similar, let's say, starting point. Let's say I have two data, like two peaks here. If I'm here, it's very hard to cross this low density region to go here, because my score function will be very, very small. So once I'm here, I cannot very easily mix. Once I'm here, I'm going to stick around. And in terms of equations, you can also see it here. So in xt, I don't make very long jumps. My epsilon is going to be a very, it's going to be a scaled down version of my score function plus some noise variable. Unless my noise variable is very large, which means I would my vector, my score function vector will be smallish. If I add very large noise, I could go all the way here and then start mixing. But I can also go there, right? So that's the problem. Langevin sampling is very local. Do you know what mixing is? So mixing is that when you sample from a probabilistic model, from a generative model, ideally you would like to have good enough coverage. You would like to have good amount of samples from everywhere there is meaningful probability. Now, when you go to prescribe distribution, like a Gaussian, that's easier because it's defined by the distribution. But when you're having not prescribed, like an energy-based model, a non-prescribed distribution, you don't really know the distribution per se, right? You only know it implicitly. So if you're defining an MCMC procedure that you sample, how do you know that you're not ignoring some part of the probability space? So that's the problem here. The mixing is slow. And that was the problem originally. So everything, score-based matching, existed since 2004, 2016, 15, 16, the first generative models were proposed. However, they were not working that great. They were promising in a way, but they were not like what we see today. And one of the big problems was that naive score-based models ignore low density regions. And we also have slow mixing, so you cannot really sample very well. The solution is to perturb with noise. And the solution is intuitive. How do we make sure that we don't have low data density areas? Well, if we add a bit of noise everywhere, then we've got a bit of probability everywhere, and then the model has something to bootstrap on. So the noise up procedure is similar, right? Here is a variational distribution, or anyways, a marginal of our true data distribution corrupted with noise, and we have to integrate over our observed distribution. The noised up data fills up the empty space, but again, if we add too much data, too much noise, that actually is a problem. So we want to use a bit of noise to make optimization better, but not too much, so that actually we start getting weird samples. Yes?
Maybe I'm just not understanding, but we had already the noise before, the CT variable that was already in some sense pushing, doing maybe not this, but something like this, and then that one couldn't be too big because I'm probably missing something, but that one couldn't be too big because then it couldn't focus anymore. But now we're adding noise over the whole thing. I'm just missing something, I think.
No, so these are works that were in parallel, right? All these papers are solving smaller pieces of the bigger picture. Indeed, this method also helps with optimization here, right? So in a way, hitting two birds with one stone. The problem is that in the naive score-based, so the naive score-based matching is the same. So the basic principle remains the same. The problem is with the naive score-based approach, you just can't do well enough in terms of optimization and in terms of sampling.
So you couldn't like in some way bump up the noise there because you already have this ZT variable.
Yes.
Could you not just bump that one up and not do? I mean, probably.
But it's the same, right?
Yeah.
So I'm just explaining why the noise now is also important for noising up. But like I will now, that's a very good point. So how much noise? That's exactly the point. It turns out you don't need just one scale of noise, but multiple. And you want to do it sequentially, adding more and more noise, but not like in one go. So multiple scales of Gaussian noise to perturb the data, so that to learn the respective matching function from below. You add some noise. Once you learn the score function, then you start adding some more. And once you converge, you start like adding more noise. And basically, this is literally like adding noise to your images. So you start from your images, you add some noise, and then some more, and then some more, and then some more. How many scales? That is a hyperparameter. How much noise you add per scale? That's also another hyperparameter. Okay. So for a single noise scale and with Gaussian noise, this is similar to denoising basically, like denoising autoencoders. And the loss becomes equivalent to, yeah, you have also here the denoising loss term. If you have multiple scales, you just have to add over multiple scales with a scaling parameter lambda that says how much this noise scale should be weighted. And like before, we start from sampling like with Langevin dynamics, we start from sampling from larger noise that we gradually decrease. Okay, so this is the pseudocode for going from 1 to L scales, noise scales. We draw one random sample. We do the Langevin, getting a new sample by moving in the direction of the score function. Once we finish for this noise scale, we reinitialize our x0 and now go to the next noise scale. Okay? So indeed, it's similar like before, but what the point is here is that you need a specific algorithm, like a specific noise adding procedure to make this work. And the intuition here is that you want the noise to be gradually added. You don't want to add all the noise everywhere because that's going to be too much variance. You add noise everywhere, so you want to learn this gradually, like in a bootstrapping fashion. You can also, here is, like this is just 2 dimensions. Imagine like 1,000,000 dimensions. So you want to focus in other words, or maybe this is, you want to add only a little bit of noise on your images in tiny steps. If I have like take a picture of a face and I basically destroy it completely, I add very strong noise everywhere, it's going to be very hard for the model to figure out what exactly is the correct data distribution. So you want to add a little bit of noise and then a little bit of noise and a little bit of noise so that the model knows how to focus around the true density regions. Is it intuitively clear? Clear enough?
I also think that maybe the decoupling, right? You have now decoupling between like how strong you learn the gradients at this point and the noise. That's it. It was pretty important.
You mean this? You mean this gradients here?
Yes.
Come again one more time.
If you did what I just said before, I realized only later, but like if you did what I said before, you would have a coupling between how you learn this gradient of this
The score function.
the score function, sorry, and this the noise that you add, because the add type will be shared. But now you don't have that. So I guess that's also.
Yeah. So how to pick this noise? Well, it's a good choice is in geometric progression. Your noise should be comparable to, like let's say the variance in your training set. So the maximum distance between your samples. So if, let's say, I mean this is the true data density. Let's say you've got a few samples. Like if you measure the distance of any two samples, you compute the maximum noise, and that's a good enough choice, practically. Again, in high dimensions, you can have very large distances anyway, so they are and equivalent, so that's a good enough heuristic. And it's usually a few hundreds or thousands, so you need a lot of noise samples that gradually increase and add until your image is completely destroyed. Here is like completely destroyed, right? And this is garbage, like that's just Gaussian noise. However, you don't want to go directly from your your exact image to the garbage. You want to garbage it gradually. Like that's the main thing. Like and this is actually almost magical, right? Like you're literally destroying an image. However, yeah, if you do it in the correct way, you can basically recover the trajectory that leads you there. We parameterize the score-based model with a unit, typically, with skip connections, and at test time, we use exponential moving average on weights. Now, a question is, all right, we've got hundreds or thousands of noise scales that we would like to consider when noising up our data, but why do we even have to hard code the noise scales? Why do we have to make it explicit? I mean, they're just a sequence, so you can think of it also as a time series, where we start from very little noise, where we add very little like noise to our pixels, and then we add more and more and more and more and more gradually. So if, like in that case, we would have like infinite noise scales. And if we do it like that, we can have higher quality samples, because we can basically learn the noise scaling, the noise procedure, the noising up procedure. We can show that we have exact log likelihoods and controllable generation. So basically, instead of having stochastic differential equations is then a way that you can actually formulate this problem. Stochastic processes are solutions of stochastic differential equations. So if you have this stochastic differential equation, it's stochastic because you have a noise variable W. You got the function of x with respect to time, so it's a differential equation, and this is a time drift. W is the Brownian motion, and it's infinite small. So from one step to the other, it follows a Gaussian distribution. That's the definition of Brownian motion. This is, again, intuitively think about it like this, and think of it in the Langevin case. D of x is equal to xt plus 1 minus xt. So xt plus 1 is d of x plus xt, and this looks a bit like our score function, and so on and so forth. And you can see this. These are the noise scales that we would normally have for our score-based models, and each snapshot corresponds to like one snapshot of our score-based function. Instead of doing it, however, for explicit discrete noise scales, hundreds of them, we do it in a continuous fashion. And because we do it in a continuous fashion, this is similar to having a stochastic differential equation. Any questions here? Maybe it makes sense to go through it and then we discuss a bit more the intuition. So stochastic differential equations are, normally you would like define your functions here, like let's say it's like, I don't know, exponential, the squared, whatever, and then you solve it. And solving it means literally applying a numerical method. So for every time step, you go to the next time step, and then to the next time step, in like in an autoregressive fashion, over small time step, over small t's, dt's. The solutions of SDEs are stochastic because every time you run it again, like every time you try to compute this, you get a different trajectory. So do you understand what we mean here by numerical solution for SDE? It's really not complex. It's basically you're saying I have, well, it is complex, but it's not complex to to understand. So let's say I've got my dx is x square plus exponential of xt. How to solve it means intuitively xt plus 1 minus xt, xt squared plus xt, then I move this over here, so xt plus 1 equals xt plus xt squared plus exponential of xt. So, okay, that's not an SDE yet, it's an ODE. SDE means that I've got also a noise variable here. So now let's add also a noise variable, d like epsilon. Epsilon. What is the solution here? So this is an SDE, literally an SDE, how we would rewrite. I made it discrete here because in practice when you solve it with computers you have to, well, you have to do it like that. So solving this means I say something, like I'm saying x0 equals whatever, 0. I compute x1. And then given x1, I compute x2. And then given x2, I compute x3. That will be the OD, solving the OD. Solving numerically, right? Solving the SD means I add also a noise at every time step. So this is numerical solving, numerical optimization. This is literally what SDEs does. And of course, SDEs, there are, you can it's a whole field on its own, like 200 years old, right? So it's a complex one, but the intuition is that, right? And sometimes there are analytical solutions, but for the more interesting and more relevant SDEs and ODEs, more often than not, you have to do numerical optimization. You have to have computers solve this in an iterative fashion. And of course, the question here is how much. Here, I assume that my dt equals 1, right? So this is literally what I did here. But you can think of it as my dt can be any very, very, very small number. Like when you take, well, when you're taking gradients, right? Like you can take gradients in very large dimension, or a very large step, or a very small step. So in stochastic gradient descent, that's why we have the lambda hyperparameter, because when we're linearizing basically the computation, we want to compute very small steps to follow the precise path. Is it clear what I mean here by the, right? So this is a stochastic differential equation. dW is Brownian motion. What does Brownian motion mean? That between two time steps, you've got Gaussian. So if you focus on one step, that's just a Gaussian noise variable. And usually SDEs are solved, as I said, with numerical methods over very small time steps.
Small time steps in that case is meant then by how much noise you add, or?
Small time steps means that dx, you don't assume that you've got xt plus 1 minus xt, but you've got a very small increment between the two, temporal increment between the two. So you have a delta t that it's less than 1. And solutions of SDEs are stochastic random variables. If you solve this SDE, you will get x0, x1, xt, correct? And if you have an SDE and you run it one more time, you will get a different. So like that's one sample, let's say. And if you run it again, because of the noise now variable, you're going to get a different sample. Every time you solve the SDE, you get a whole new different trajectory. So that's why the solution, this is a solution. Solution means literally computing the value x for every time step. So these solutions are random variables themselves. They're random variables because they're taking different values every time you run them. And they form trajectories over time. So these are the trajectories that you've got here. Correct? What time is it? Okay, we're running out of time. The PDF of xt is p tx in the subscript. In the discrete case, you'd have, instead of t, you have an explicit noise scale. The only difference that t is continuous, takes a continuous value, whereas here you have a discrete value. P0 is your data distribution, like data space distribution, and P capital Tx is the distribution after all the noise is added completely. So it's your prior, let's say. So in score matching, the SD is the generalization of having a lot of a lot of specific finite scales. In the discrete case, we perturb with hand-picked noise scales using a geometric progression. So we literally have to define in our config file, okay, these are our noise scales with this particular like maximum noise per scale, per scale, yes. Whereas now the noise scale is controlled by the stochastic differential equation, and in this case, our hyperparameter is which one is the which stochastic differential equation are we going to use to generate our noise. Now, if we have this SDE, our Gaussian noise grows exponentially with time. That's the noise variable, and this is it grows exponentially. So for every new t, we have to add the previous. The type of stochastic differential equation is open. You can do whatever you want. Of course, some works better than the others. Noise-conditional score matching is similar to this type of SDE. So in the discrete case I and I minus 1, the subscript, the two noise scales I and I minus 1, that is similar to having d of x and d of the square root of the noise scale. I will come back to the derivative you mentioned before graphically afterwards when we have time, okay? Because I think it was something missing there. But this is, like, let's say intuitively the connection between discrete and continuous scale. Yes?
You also, because in numerical solution you normally take like multiple steps in the past, and you don't use the less time step. Like, is there also like SDEs that you use?
Yes. So people have also tried having better solvers. If I remember correctly, that doesn't really seem to be making a big difference. I mean, it's not like, or you can learn, like you can learn the noise schedule more precisely. In practice, it doesn't even work. I mean, work, but not necessarily better. So you add complexity without adding really benefit. Another one that works pretty well is this. It looks really scary and whatever, but basically, again, it's a numerical solver that solves it. So in the end, we really just need to separate this and make, pass it to the numerical solver, and then the numerical solver just does it for us. The process of going from the data to noise is very straightforward. We just add more and more noise, and the noise is controlled by our SDE. So there is basically little for us to do. We just do this, we just for every previous step. So in the beginning, x0. Well, now this is the reverse, but we start from x0, our data. We add one step of noise, right? And then again, and then again, and then again. We just add noise, literally add noise. There's no complexity there. Until our images, or like my face, starts looking a pure Gaussian noise sample. So it's very easy to make noise from data. Of course, the question is, how can we now do the reverse? How can we go from noise back to data, the reverse process? And it turns out that specifically for SDEs, for any forward SDE, there is a reverse SDE that has the reverse trajectory, and the reverse SDE has this form where the score function appears. Which is great, because then we can have our neural network trying to imitate the process of, reversing the process of adding noise. So that's the forward case from x0 to xt. Literally, we start from an image, x0, I sample dog. So that's my dx. My dx is that's the definition, let's say, over okay. I don't want to confuse with a notation here, but anyways, like this is the intuition, right? So we start from x0. This is the way we define the next step, like what our sample should be looking in our next step. Oh, sorry, here. So we add noise and perhaps a function of our current data. Like that's it. We literally add noise. There is no learning here. And in the reverse, we just need to make sure to optimize this equation. So we want to optimize an equation that contains a score function. And by doing that, we can arrive at good models. So how do we learn this? A neural network approximates the score function here. We take an initial sample from the prior distribution. So let's say this is our Gaussian. We take an initial sample, and we solve the reverse. So we pass it again to the numerical solver till the model matches the data distribution. So we want, in the end, our final model output here to be very close to the data distribution. This can be shown that it is equivalent to optimizing this like elbow. And the intuition here is that if, like this is the score matching. So this is the score matching objective that we can obtain in the process. Similar to what we see we have with the discrete scales. We've got the score matching here. Note here we're sampling time steps, so we don't have to solve exactly the whole reverse SDE. We just sample one of the time steps, so one location from the trajectory. So if that's like our trajectory, we don't really have to go from xt to x0. Like that would be normally required if we were doing numerical optimization. But here we don't do per se numerical optimization. We just need to sample a time step. So let's say if for simplicity we say we have time 0 to time 1, just rescaling, and then our time steps are any continuous values between the two. We sample one randomly, like 0,537. Then we take an expectation, so we sample a data point from our score function using that particular time step. We try to minimize the usual score function like type of objective, and we have this KL term which says that which compares our prior, our Gaussian distribution, sorry, our learned prior with the true prior. If we have perfect score matching, like here, and if we can match the prior, we approximate the data distribution. So here, again, it's what I said before. This is time-dependent score matching. So instead of having, you can think of it in the previous case with the discrete scales, instead of having all the 100 scales, we sample one of them, and we optimize, and that's it. We don't have to do all of them. Well, that would be particularly hard for the infinite case because we cannot do infinite time scales, and solving this with numerical solvers would be impossible or extremely expensive anyways. We have to have a weighting factor here, which tells you how important your time is. So some time locations will be better or worse than others. We sample from our training set and optimize the score matching. Yeah, we optimize our score matching approximation. What time is it? We're dangerously almost out of time, so I'm gonna go very like that. These are not super important, and I'm going to but again, here I'm saying that the reverse SDE, solving the reverse SDE is literally, once we've got the optimal parameters, so once we've got like this sampling of time steps and stuff is for training the model, right? Now, how would we sample? Let's say this is trained, like let's say magically something got trained, right? So it means that we've got super good parameters for our score function. How do we go from here to here?
we use noise as input,
Yes,
and predict probability.
exactly. We solve the reverse SDE using a numerical solver. So now we don't sample anymore because that's during training to approximate, to make it faster and approximate. We just sample from our prior, like a Gaussian, and we pass it to our SDE. Reverse SDE, forward SDE, doesn't matter. Like for the numerical solver, it's just an SDE. We pass it to the SDE and computes the steps again and again. So this is the forward process. The reverse process would be basically starting from a random location here until it goes to an image. Of course, with better sampling procedures and architectures, we have SOTA generation, state of the art, like really good generations. Now with Langevin, MCMC, and SD solvers, we don't really get exact log likelihoods. That can be a problem. It can be shown that we can get an ODE in the end, and with which we can have the precise log likelihood. And these are some very nice examples, and by now you know that they're even better, and so forth. Very quickly over diffusion models. Now score matching and diffusion are very similar in many ways, and if you actually check blogs and papers, you will see very direct equivalences. Happy to discuss more offline, but let's say the conclusion was the same, so the type of model was the same. The starting point, the inspiration was different. Diffusion models define also a forward and reverse diffusion process, and diffusion processes are actually ODEs and SDEs. ODEs. Here again, T is equals 0 is the data distribution. T equals capital T is the prior distribution, the noise distribution. You got a forward process, so where you're computing your conditional from any time step T to, well, T minus 1, because we'll go to x0, or we've got a variational, let's say, parallel, let's say, distribution from T minus 1 to T. And the basic idea here is we want to match the two. So what we want to say here with the diffusion models is for every time step, we want our conditional distribution from when going from T to T minus 1, so from our noise to our observations, to be equal to the opposite. So for the forward diffusion process, we got a Gaussian. We consider every time step to be independent. So xt is conditioned only on T minus 1, not other T minus 2, T minus 3, and so forth. And when we've got the complete data distribution, it's a product of all the individual ones. So we assume Markov independence here. And the interesting thing here is that if we put like all these things together, so we write xt with respect to xt minus 1 plus a noise variable that comes from our Gaussians, we can rewrite any time step t as a linear combination of our data plus some form of the like more complex version of our noise variable. Sorry for that. And for this, we're using, like to derive this, we're using the fact that we're having explicit Gaussian distributions in the process. Now for the reverse diffusion process, the method was using a variational inference, trying to minimize the KL divergences between each pair of time steps. That's it. So for the prior distribution, it's like xt x0. And the prior distribution. For any other small step t, we've got a similar KL divergence. And since we have Gaussian distributions, the KL terms can be computed in closed form. And this is actually what is so nice about diffusion models, basically. So here we're sampling a data from our training set and noise variable. And in effect, diffusion models, what they do is they learn to predict the noise that we added in the transformed signal. So we add noise to our sample, and the model tries to predict what was the noise that we added, given our image. So I pick an image. I add noise. The model doesn't know, of course, what is the true image and what's the true noise, and it tries to figure out what was the noise that you added at each time step t, right? So this is our model here. X0 is the image we sample from our training set. We add a noise.
Sorry, wij gaan nu beginnen met onze les.
Once the end. Okay, I'm done. And that's it. That is the diffusion models. They try to literally predict the noise we add per step. It has very good trajectories and great qualitative results. And yeah, this is it. Thanks.